Today's lecture is going to be in Chapter 12, dealing with Section 12.5 on ionic bonding and structures of ionic compounds. Structures of ionic compounds. Ions are packed together to maximize the attraction between ions when they're in compound form. This structure represents the ions that are packed as spheres. So we see lithium, which is smaller than fluorine, and they're packed in there, and you notice it's alternating so that the negatives and positives are attracted to each other. This structure shows the position or centers of the ions, and the sphere ions are packed in a way that maximizes ionic attraction. Cations, when we look at the cation compared to its atom, cations are always smaller than the parent atom. Here we see lithium and lithium ion, sodium and sodium ion. Anions, on the other hand, are always larger. Here's fluorine, and here's the fluoride ion. You notice the size difference. This size difference should make sense, actually. Remember that lithium, in order to form a +1 ion, had to lose an electron. Well, the positive force in the inside of that nucleus is just the same in the lithium atom as it is in the lithium ion. But we have fewer numbers of electrons to pull toward the nucleus. So while this one has 3 electrons to pull toward the nucleus, lithium ion only has 2, so that pull is tighter, therefore making the radius of the cation smaller. And it's the same in all of these. On the ions that form anions are negative, it's just the opposite. You notice with the fluorine atom here, we have 9 protons and 9 electrons. The fluoride ion has gained an electron, so the pull on those individual electrons is a little bit less than it was in the atom form because there's one more electron than there are protons to pull them toward the nucleus, so the size gets larger. Isoelectronic series. This is a series of ions and atoms that contain the same number of electrons. Iso meaning the same, electronic dealing with the electrons. So if we look at oxygen, ion, fluoride, neon, sodium ion, magnesium ion, and aluminum ion, they all have the same number of electrons when we look at them. So they're considered part of an isoelectronic series. So this says to choose an alkali metal, an alkaline earth metal, a noble gas, and a halogen so that they constitute an isoelectronic series when the metals and halogens are written as their most stable ions. So I'm going to pause it here, or this is a good place for you to pause it, and to come up with this to be able to answer the following questions. So I'm just going to go ahead and choose 4 of these, and then we'll walk ourselves through it. So an alkali metal, an alkaline earth metal, a noble gas, and a halogen that have the same isoelectronic series. For an alkali metal, let's have sodium. Sodium forms a +1 charge, and magnesium, which is right after sodium, forms a +2 charge. And when they lose their electrons, they become like the noble gas before them, which is neon. So the halogen that becomes like neon is the one that's right before it, and it's going to be fluorine with a -1 charge. So here's our alkali metal, our alkaline earth metal, our noble gas, and our halogen that have the same isoelectronic series when they form their most stable ions. So what is the electron configuration for each species? They're all going to be the same as neon. So if we look at neon, we know it's going to be 1s2, 2s2, 2p6. And that's going to be the same electron configuration for all of these. Determine the number of electrons for each species. So there's 6, 7, 8, 9, 10 in this series. The number of protons for each. So sodium is going to have 11 because that's its proton number. Magnesium is going to have 12. Neon is going to have 10. And fluorine is going to have 9 protons. Rank each species according to its increasing radius. Well, we know that positive ions tend to lose electrons and become much smaller, while fluoride ion is going to be larger because it gained an electron. I would say that the smallest would be magnesium, then sodium, then neon, then fluorine. The next concept check says to rank the following from smallest to largest atomic radius. These are all isoelectronic, an isoelectronic series, so have the same number of electrons in them. So when we look at them, what we have to look at is the nuclear charge. So the larger the nuclear charge, since they all have the same number of electrons, the larger the nuclear charge is, the tighter that those electrons are held into the center of the atom, so we have a smaller radius. So in this case, this would be the answer because calcium has the highest nuclear charge, even though they all have the same number of electrons, so it holds those electrons that it does have much tighter than the sulfur would in this case. So this would be the correct series for the smallest to the largest atomic radius. The final concept check says which atom or ion has the smallest radius. Well, we're talking about oxygen, so the nuclear charge in the center never changes. But remember that the fewer electrons that the same number of protons have to deal with, they get pulled in even tighter. So in this case, we have oxygen that's lost 2 electrons, oxygen that's lost 1, equal numbers of electrons and protons here, and this oxygen has gained 2 electrons. So the one that's going to come in and have the smallest radius is going to be the one with the fewest number of electrons. So in this case, is the oxygen if it were possible to do a +2 charge on that oxygen ion. Let's take a look at ionic compounds containing polyatomic ions. Polyatomic ions work the same way as a simple ion, and the covalent bonds hold the polyatomic ion together so it behaves as one unit. So polyatomic ions are held together by covalent bonds, and they act as if they are one unit that is ionic. That takes us through section 12.5, and we'll be ready to start Lewis structures in the next lecture.